So today's talk, I was going to talk about causality in genetics when good methods go rogue. So thinking about how to approach causality in genetics and when to perhaps be cautious or think about the assumptions being involved. So the first question with causality in genetics, I think, should be what could possibly go wrong? When you start to think about causal inference in the field of genetic association studies, are there potentially more issues than you do have in a standard association study? Answer, yes, there probably will be more potential errors or pitfalls, and you can think about that for several reasons. So one study's approach may not be valid in another, and this is particularly true with genetics, where there might be issues with heterogeneity in your study that aren't true in other studies. So maybe a published study didn't have to correct for batch or study effects, but you do, in which case you need to kind of approach it differently. Also, statistical methods evolve over time. This is particularly true right now with machine learning and Mendelian randomization. There's so many statistical approaches coming out. It can be kind of hard to keep up with the field. Also, not everything that's published is valid. This can be kind of interesting to think about, but in September 2022, and this kind of blew up around Thanksgiving about a year ago, Hyundai, it's a parent company of Wiley, sorry, started to retract more than 500 papers. And one paper in particular, like, really blew up on Twitter for kind of a funny reason. So if you look at the plot on the left, this is kind of your standard box plot, and the error bars look reasonably normal. The paper that got all of this press involves the graph on the right. And if you look kind of carefully at the error bars on the graph on the right, they look a little different. They're actually a capital T copied and pasted over every error bar. They're not actually the real error bars. And it's funny because one of the biostatisticians who works with me was like, that's just lazy. They should have used a different font. I was like, I don't think that's the moral to take away from this. But this paper got published, and clearly there's an issue with the error bars. There were other issues in the paper, one of which was the data availability section said that they didn't even have data in the study, despite the fact that the entire paper was publishing on data. And there was so many things obviously wrong with this paper that it blew up into a whole discussion of how did this get published. And it's a real problem because if somebody looks at this paper and uses it the baseline for their study, there are going to be problems associated with it because there's problems associated with this paper. And I'm not saying this happens a lot. I just thought that was kind of an interesting Twitter argument. Every so often there's statistical arguments, or X, sorry, that it can be interesting. Also, with causality and genetics, there's a level of complication. So we're now no longer thinking about association. No, we're now thinking about causation. And of course, the famous saying, association does not imply causation. As you can see in the little statistics cartoon, you might think correlation implied causation, took a statistics class, now realize that that's no longer true. Did the statistics class help? Who knows? Just because they're associated, we can't tell. Also, when thinking about correlations, there can be a lot of reasons to have spurious correlations. There's this wonderful website on spurious correlations where they show essentially that the time component can produce correlations between things that probably shouldn't be correlated or aren't correlated for a causal reason, that are kind of fun. So this one, the black line is the consumption of margarine, and the red line is the divorce rate in Maine. And if you look at the plot alone, they're very correlated, very strong correlation. And then, of course, you don't want to walk away with the wrong message that for some reason there's a causal trend here. Who knows? But because of that time component, we see a very strong correlation between things we wouldn't think. A lot of fun examples on that website. There's even one with like venomous spiders and the number of letters in the spelling bee, National Spelling Bee. So quite fun. So for causal inference in genetics, there are a lot of different methods and different ways of thinking about causality. And a lot of times we do want to think about causality because it's not just whether the SNP is associated with the outcome, it's is the SNP causing the outcome? How is the gene or the SNP acting on the outcome, maybe through other traits? So we want to start to think about causality. And there's two popular classes of methods for causality in genetics. One is mediation analysis, and the other is Mendelian randomization. I would say of the two, Mendelian randomization, or MR, has become much more popular. If you go to the American Society of Human Genetics conferences, you just can't avoid MR. These days, it's very popular. And then how kind of are these two approaches working? So if we think about depression and alcohol use, we have genes. And within our genes are single nucleotide polymorphisms, or SNPs, that maybe cause depression. And we have SNPs that also cause alcohol use. And then we might want to use those SNPs to see if depression causes alcohol use. Can we establish this arrow here? Or it might be the case that alcohol use causes depression. So maybe the arrow goes in the other direction. Or it could be the case that depression causes alcohol use causes depression, and depression causes alcohol use. And we have a cyclic relationship or a bidirectional relationship. So MR is kind of focused on establishing these arrows here and using the SNPs to see if we can establish those arrows. Versus with mediation analysis, we might be more focused on seeing how the gene acts on our outcome, let's say alcohol use, through mediator depression. So if you have these SNPs associated with alcohol use, are they only associated because of depression, or is there an alternative pathway? And how much of that path can you say is through depression? And so we might want to decompose in that fashion. But of course, there's always caveats associated with that. So if we start to think about our mediation analysis, we have different ways to approach this. So mediation analysis, you can think of in a causal inference framework. So either using your counterfactuals, or you can think of Barron and Kenny of more of your standard regression framework. I usually lean more towards the counterfactual framework, because the regression framework can be limiting in some regards. But either way, when we think about our directed acyclic graph, we can think about the effect of our exposure A, so then in our case here, it'd be our SNP, on our outcome Y, let's say alcohol use, through our mediator M, depression. So in our example, we think that the SNP causes depression, depression causes alcohol use, and then we want to kind of decompose the effect. So how much of the effect is through this indirect pathway, and then how much is through the direct pathway of A on Y? But the problem with this is there's several assumptions we're making. One is no unmeasured confounding, that any confounding of the exposure mediator outcome relationship we've accounted for. There's a lot of sensitivity packages to see how realistic this assumption is. Also, no measurement error associated with the mediator or the exposure. And then the third assumption, which is one that sometimes gets overlooked, is that this directed acyclic graph is correctly specified. So in order to kind of look at this relationship, we have to assume that these arrows were correct. And especially in our example, we're already not sure about the direction of the arrow from our mediator, depression, to our outcome, alcohol use. And sometimes, if you're not sure about the direction of this arrow, at one point, or some investigators, what they started doing is saying, okay, we're not sure about the direction of the arrow, so we'll do the mediation analysis twice. We'll do it once with depression as mediator and alcohol use as the outcome, and then we'll do it again with alcohol use as the mediator and depression as the outcome, and then use the results of the mediation analysis to dictate which way we think the direction of the arrow goes. And we've done some work on this because theoretically it doesn't hold up. And then also with simulation studies, you can show quite easily that this is not a good approach to do, that you can't just run the mediation analysis twice to infer the directionality of that effect. So you can see that here with our DAGs, because if we look at the effect here of the SNP on now M, this would be depression, through alcohol use Y, if it is true that M causes Y, by switching the role of the mediator and the outcome, now Y is a collider on the path from our exposure A to our outcome M. So what does this mean when we have a collider? Well, what happens with a collider is if we do nothing, so we see the two arrows kind of coming together, then that path is blocked. But if we condition on Y, then that will unblock that path and we'll now see an association. So colliders can create issues. A great example of colliders are rain and sprinklers. So kind of a classic example that if you go outside, there should be no association between it raining and the sprinklers being turned on. It's not like turning on your sprinklers make it rain, although it'd be cool if it did, but no association. But a collider on the path would be whether the grass is wet. So if you go outside and you touch the grass and it's wet, then you automatically know it either rained or the sprinklers turned on. So once we condition on that, we now see an association. So we'd have problems with our collider on the path. So what happens here, and we can see in our simulations, so we simulated a bunch of direct and indirect effects. So first starting, we generated an exposure A to have an indirect effect on Y. So essentially here, we generated only this path. So we have A acting on M through Y, so we have our indirect effect, but this path here from A to Y not existing, so no direct effect. And if we do that, then we see that we have an indirect effect, this red line, if we correctly specify the mediator and the outcome. But if we incorrectly specify the mediator and the outcome, switch the roles, then we see a direct effect, but no indirect effect, this blue line. But we see no direct effect, the black line, if we correctly specified. So essentially they switch. You'll think that there is an indirect effect if you correctly specify the mediator and the outcome, but if you incorrectly, you'll think there is a direct effect. Versus for our simulation studies where we generated a direct effect but no indirect effect, our black line, where we correctly specified the mediator and the outcome, we see their direct effect, and we see no indirect effect. Versus the blue line, when we incorrectly specified our mediator outcome, we think there's an indirect effect, but no direct effect, the green line. So they switch. So if you look at these first two scenarios, it starts to seem possible that maybe you could use mediation analysis to infer the directionality between the mediator and the outcome if there's only a direct effect and no indirect effect, or vice versa. But even then, it wouldn't be clear which was the true scenario and which wasn't. But when we generate both a direct effect and an indirect effect, then as you can see from these lines, you just can't tell. Both methods are returning a significant direct and indirect effect, and there's no way to decipher the directionality between the mediator and the outcome. So this was kind of some of our work just showing that you have to be careful with the direction of that arrow, and which nicely leads into MR, or Mendelian randomization, which is very focused on that arrow between alcohol use and depression, or in the case, our mediator and our outcome. So Mendelian randomization is answering somewhat of a different question. So with mediation analysis, we were interested in looking at the effect of the SNPs on the outcome through the mediator. So how much of the effect was through the mediator, the indirect effect, or how much was not, the direct effect. But with Mendelian randomization, you're approaching it from a different point of view. Now instead, you're using the SNPs, your G, to tell you something about X, your exposure, in order to say, instead of just is X associated with Y, but does X in fact cause Y? So we're using these SNPs as our instrument variables to say something in terms of causation. And so MR kind of helps take one step from association into causation, but of course, we're making a lot of assumptions in order to do that. So the motivation here was that originally thinking about George Davy Smith and MR more from I think the 70s and 80s. Originally, they were thinking that you might have an exposure such as smoking, and smoking has a lot of measurement error with it. But there's a bunch of SNPs associated with smoking. So maybe instead of using smoking by itself, you can use the SNPs, which you don't necessarily have the same level of measurement error, in order to tell you something about smoking. And then, if it's true that these SNPs can be used as a proxy for the smoking variable, if the SNPs are associated with an outcome, say lung cancer, then that would be letting us know that smoking causes lung cancer if, and this is a big if, the only path from the SNPs to the outcome is through this exposure variable. So there's no pleiotropy. If we had a path from G1 into Y, that would be pleiotropy, and then that would be problematic. But there's some advantages in this framework, one of which is we can have measurement error associated with X. Also, there can be unmeasured confounding between X and Y. And we can say something in terms of causation. But there is a lot of controversy over whether the methods and the assumptions are being met. And then there's been a lot of methods coming out since then that expand out, and we have different assumptions with them. So one of our advantages with MR, we can determine if the exposure causes the outcome. So we can start to say something about causation potentially. Also, depending on the approach, robust to any unmeasured confounding of the exposure outcome relationship, which is a big stumbling block in mediation analysis. Also, robust to measurement error of the exposure. Disadvantages with MR depends very heavily on the MR approach being used. So most of the MR methods, especially IVW, the inverse variance weighted method, the weighted median method, and the MR-Egger approach, the three most popular approaches, they all assume the only path from the SNPs to the outcome is through the exposure, that we don't have any pleiotropy. Although MR-Egger does check for pleiotropy, it's not necessarily completely adjusting pleiotropy. Also, that there's no SNP exposure interaction on the outcome, which may or may not be true. And also some of the methods, especially IVW, they're assuming that all of those SNPs are valid instrument variables for the exposure, which may or may not be true, especially depending on how the SNPs have been chosen. So within our MR framework, they've kind of expanded out. So standard MR, we're very much focused on establishing if exposure causes the outcome, or if phenotype 1 causes a phenotype 2. But in this framework, we're very much assuming that this arrow is correct, that it is actually true that phenotype 1 causes phenotype 2, and you're just trying to establish if the arrow is there, not necessarily the direction of the arrow. But there have been MR approaches that kind of extend out further and say, not only are we going to establish if this arrow is here, but in fact, the direction of the arrow. Is the arrow going from phenotype 1 to phenotype 2, or is it going from phenotype 2 to phenotype 1? So MR-Steiger is a very popular approach and very flexible to test this effect direction. And it does it using a two-stage approach. So the first stage is just using MR. So classic MR, and it's saying I'm going to take a SNP set, say SNP set 1, and then I'm going to look at an MR analysis for phenotype 1 is the exposure and phenotype 2 is the outcome, and use this to see if there is a potential causal relationship. So this is to establish if this arrow potentially exists. Then for part 2, in order to establish the direction of the arrow and the confidence surrounding that direction, they use the Steiger z-test. So what they're doing is they're looking at the correlation between the SNPs in phenotype 1 and the SNPs in phenotype 2, and then looking at the difference of those correlations. Because if the SNPs at 1 causes phenotype 1 and phenotype 1 causes phenotype 2, then the correlation between SNP set 1 and phenotype 1 should be stronger than the correlation between SNP set 1 and phenotype 2. because there's no other path than either through phenotype 1. So we can use the Steiger z-test to calculate the difference in the correlation between the SNPs in phenotype 1 and the SNPs in phenotype 2, and use that to establish the direction of the arrow. And then this approach originally was focused more on determining bidirectionality. Now it's being used a lot more for filtering SNPs before the MR analyses. So before running kind of a classic MR analysis, you want to maybe filter out any SNPs that are pleiotropic or have a bidirectional effect, or if there is a bidirectional effect. And so it gets used in that regard. So what we were focused on was kind of the assumptions going into the method and when the method was most likely to break down. So the three main assumptions going into the MR Steiger approach or problems are that the SNPs cannot influence phenotype 2 through some other pathway. So if there's any sort of pleiotropy, if we come back here, if there was an arrow from SNP1 into phenotype 2 that didn't go through phenotype 1, then we would have pleiotropy, and we could potentially infer the wrong effect direction between phenotype 1 and phenotype 2. Also, measurement error of the phenotypes. We could potentially infer the wrong effect direction as well, and any unmeasured confounding between phenotype 1 and phenotype 2. So our goal was to explore when the MR Steiger approach was able to infer the effect direction correctly or when it didn't. And we were mostly kind of focused, one, on pleiotropy, because we feel it comes up a lot in data analyses, but also the unmeasured confounding, because standard MR approaches are robust to the unmeasured confounding of the phenotype 1, phenotype 2 relationship. So we were interested in how that was affecting the MR Steiger approach. So we did this through simulation studies, and we simulated a whole bunch of different scenarios, created an R package so other people could look at other scenarios as well. Our first scenario we focused on was A. So A is kind of, let's call it best case scenario, that the SNP only acts on the outcome Y through our exposure X. So there's no alternative pathway, there's no measurement error, there's no unmeasured confounding. Kind of the best case scenario is A. B is pleiotropy. So we have the effect of G on Y through X, but also a direct effect of G on Y. C, we have measurement error. So there's some sort of measurement error associated with X. D, we have measurement error for X, and we have pleiotropy, so the two paths. E, we have unmeasured confounding, so unmeasured confounding of the XY relationship. F, unmeasured confounding and pleiotropy. G, measurement error and unmeasured confounding. And H, we have everything. We have measurement error, we have unmeasured confounding, and we have pleiotropy. And so for our simulation studies, we wanted to match kind of closely what was done in the original paper. So we generated N subjects and the SNP G from a binomial distribution with a minor allele frequency of 50%. Our phenotype 1, our X true, we generated from a normal distribution, such that the mean of X true is gamma naught plus gamma GG for our SNP G. Our phenotype Y is generated from a normal distribution as a function of X true or phenotype 1. If there's no measurement error, then we set our measured phenotype 1 X equal to our X true. If there was measurement error, then we generated our measured phenotype 1 X from a normal distribution such that the mean of X is our delta naught plus delta X true. And then if there's pleiotropy, we generated our Y as a function of X true, our exposure, and G, our SNP. So we have both the indirect and the direct effect. If there's unmeasured confounding, then we generated U from a normal distribution, and X true is a function of the SNP G and the unmeasured confounder U. Y is a function of the exposure of the X true and the unmeasured confounder U if there's no pleiotropy. And then if there is pleiotropy, it's a function of X true, the SNP G, and the unmeasured confounder U. And then we matched, for one of our sets of simulation studies, similar to the MR-Steiger approach, 100 subjects. Our second simulation set, we went with more subjects because 100 for genetic studies is really low. Set the intercepts to 0, delta G to 1, beta G, genetic effect size, to 1 for pleiotropy, delta U and beta U for the unmeasured confounding to 1, and we varied beta X. And so for our simulation studies, we started to see some interesting trends, we thought. So our first scenario A, this was kind of our best case scenario. So no pleiotropy, no measurement error, no unmeasured confounding, kind of the best case scenario, which may or may not be true. And here we were looking at 3 outcomes. So outcome 1, the black line, is case 1. So this is that the method concluded that X caused Y. And we did generate X to cause Y. So we're hoping to see the black line. The red line is the incorrect conclusion. This is that Y causes X, which is counter to what we generated. And then the green line, 3, is inconclusive. So this is when the method says it's neither case 1 or case 2. We don't know. It's case 3. So what's interesting here is we generated X to cause Y and are perfectly meeting the assumptions of the MR-Steiger approach. But as you can see, initially, we're able to detect that X causes Y for the proportion of simulations, and then it starts to drop off as beta X increases. So what happens is, as the correlation between X and Y gets too strong, then the Steiger z-test is no longer able to detect a difference between the SNP and X correlation and the correlation of the SNP and Y. And so it can't infer the direction of the effect, which makes sense. If there's too much of a correlation between X and Y, it would be hard to infer the directionality of that arrow. So we start to see it increase and then decrease. And then over here, we're looking at our test statistic being greater than 0, our p-value for the Steiger z approach being less than alpha, and then the MR p-value. So even though the p-value from the MR analysis is very strong and we're rejecting null, we see that as the correlation between X and Y is starting to increase and increase and increase, then the Steiger z-test is no longer going to reject. And now if we introduce B, so we have pleiotropy, no measurement error, and no unmeasured confounding, then all of a sudden, the MR-Steiger approach is inferring the wrong effect direction. So it's now saying that Y causes X, when in fact it was generated such that X causes Y. And we see that very consistently, the wrong effect is being detected. And that's because, as we can see here, we're getting the wrong effect from our Steiger z-test. So then when we have no pleiotropy, measurement error, and no measured confounding, we started to see that we're still seeing the right effect direction with the MR-Steiger approach for most of the scenarios, although as you get out here for a very high increase in beta X, it starts to detect the wrong direction. And then for a lot of the simulations too, it's inconclusive. For the pleiotropy measurement and no unmeasured confounding, we see that it's mostly returning the wrong effect direction. Then here with our no pleiotropy, no measurement error, and unmeasured confounding, mostly returning the right direction if something's other than inconclusive. But mostly, as you can see here, it's saying that the results are inconclusive. It just can't tell if X is causing Y or not. And then once we introduce pleiotropy, the no measurement error and the unmeasured confounding, either inconclusive or the wrong effect direction. And then for the no pleiotropy, the measurement error and unmeasured confounding, it's mostly inconclusive or the right effect direction. And then once we introduce the pleiotropy again, then we're seeing the wrong effect direction or inconclusive. So especially for the simulations we were focused on here, we were seeing that pleiotropy was really affecting the ability of the MR-Steiger approach to tell the right effect direction. And so that assumption of pleiotropy is very necessary and also may or may not be quite an issue. It just depends. So we wanted to see with a real data example what we were seeing, because with the simulation studies, you're hoping that you're inferring the right scenario, or that maybe your simulation studies are true to reality, but it's not always quite clear. So here for our COPD gene study, we looked at 6,659 subjects with European ancestry, and we wanted to see if 8 SNPs were valid instrument variables for pack years of cigarette smoking, and to look at the effect of pack years of cigarette smoking on FEV1. So you would think that pack years would cause FEV1, that a long history of smoking would cause FEV1, but maybe not necessarily true. And the SNPs we were looking at, these ChRNA 3 and 5 are in the chromosome 15 region. So is IRAB2, ChRNB4, and AGPHD1. And then the chromosome 19 region, we have the CYP2A6, CYP2A7, and CYP2B6. And these are all regions that have previously been associated with both smoking and lung function. And so that's why we thought they'd be good candidates, because potentially there was maybe issues with pleiotropy associated. We're not sure, but there's definitely been associations with these regions with both smoking and FEV1 in other studies, and in particular in the COPD gene study. So looking at the single SNP models, adjusting for age, sex, and genetic ancestry via principal components, the MR Steiger approach was inconclusive about pack years causing FEV1 for the chromosome 19 SNPs, but for the chromosome 15 SNPs, we were seeing that FEV1 was causing smoking status. And so it's kind of an opposite direction of maybe you would have thought. And so this was kind of interesting results. And like we said, it could have been due to pleiotropy, it could have been due to something else, but it does demonstrate that, you might need to be cautious with the MR Steiger approach, especially for the single SNP models. So when only looking at one SNP at a time instead of the multiple SNP models. And so then from that, we were back and forth in touch with Jib Hermani and some of the original authors of the MR Steiger approach. And they were telling us that there was kind of potentially issues with unmeasured confounding in the MR Steiger approach. So originally, we didn't think that the unmeasured confounding would be an issue, because when you think about your directed acyclic graph and your standard MR approaches, that the effect of the SNP on the mediator, then to the unmeasured confounder, then the outcome, that mediator would be a collider on the path, and which would potentially be robust unmeasured confounding. So it shouldn't maybe be an issue. But because MR Steiger is looking at the difference of the correlation between the SNP and the exposure and the correlation of the SNP and the outcome, it's kind of creating this weird issue where if you have unmeasured confounding with different signs, so say the unmeasured confounder is positively associated with the exposure X, but negatively associated with the outcome Y, then what can happen is it can create this association where the variance between the SNP G and the exposure X increases, but the variance between the SNP G and the outcome Y decreases, such that the absolute value of the correlation between the SNP and the exposure X is less than the correlation of the SNP and the outcome Y, which is like crazy. I mean, I can't tell you how much coffee and directed cyclic graphs we sat down with before we could fully understand this. And so our next paper we were writing up was on how if you have this unmeasured confounding with the different signs, then as we can see in the plot here for our simulations, you'll have the correlation of the SNP and X less than the correlation of the SNP and Y, the absolute correlation. And then you can see the blue line there, you'll infer the wrong effect direction. And so this is potentially a problematic issue, because it's really not clear how much this would happen in reality, because it's unmeasured confounding. So this is something you didn't measure. So it's not always clear how strong of the association the unmeasured confounder would be, and also if it's in a different effect direction. So then the original group wrote a paper about our paper talking about how there was potentially selection bias. So when we showed the data example before with COPD gene and said, maybe FEV1 causes pack years, and that's what MR Steiger is saying, and that this maybe could be a result of pleiotropy. They were saying that actually it could be a result of selection bias and that there could be problems with the MR Steiger approach if there is any sort of selection bias with your studies, which potentially could be an issue with most studies. So for the COPD gene studies, this was a study of current and former smokers. So everybody smoked at least 10 pack years, and it was a case control study of COPD. So some people had COPD, some people didn't, but everybody in the study was a very heavy smoker. So there's a lot of selection bias going on here. This is not a normal sample. So they were mentioning that maybe it made more sense to look at the UK Biobank. But when we looked at the UK Biobank, which potentially doesn't have the selection bias because this is a large population from the UK, although there have been studies saying that there is some selection bias, we were seeing similar issues when we looked at the single variant analyses. So when we looked at the single variant analyses, especially chromosome 15, when we looked at the ever versus never smokers in the UK Biobank with FEV1 FEV1 also from the UK Biobank, we were seeing the wrong detection or direction detected. When we looked at quit smoking for greater than 6 months, we saw mostly the right direction detected or not, but none of it was really significant. Then when we looked at cigarettes per day from the Luminol paper, so this is not the UK Biobank. So the outcome is generated from summary statistics from the UK Biobank from FEV1, but the cigarettes per day was generated from a meta-analysis. Then the right effect direction was detected. But interestingly enough, COPD gene was one of the studies in this paper. But then when looking at former versus current smoker in UK Biobank, the wrong effect direction was detected potentially and rather strongly. And so this just highlighted that with the MR Steiger approach in particular, you have to be very, very, very careful with the single SNP model. So the original authors were saying, and we agree with them, that looking at the one SNP at a time in order to infer that effect direction can potentially be very problematic. And you should maybe use multiple SNPs, but there's also potentially still issues with pleiotropy and selection bias and unmeasured confounding. So the method gets used a lot for filtering SNPs going into the MR approaches for that reason, to try and pick up on these different assumptions. So the conclusions from kind of the 4 different papers we were highlighting and the different approaches is that caution's needed. So I feel like it's always good to be cautious, but especially when you're trying to think about causation instead of associations, there's additional assumptions being made. And especially in our genetic association studies, these are assumptions that maybe are not testable. So when we were thinking back to the mediation example, you don't really know if depression causes alcohol use or vice versa. So using the mediation framework maybe might not be the best for that example because you need to know which way that arrow goes and you might not know. And then in MR, especially with MR Steiger and trying to infer the direction of that arrow, it could be an issue if there's pleiotropy. Also, if there's any sort of unmeasured confounding, it can very much be an issue depending on the signs of the association, which it's unmeasured confounding, so you can't exactly test. And so it can be hard trying to infer that unknown effect direction. And so I think in general, it's always good to have a bit of caution when approaching these methods and thinking about whether they really work for your study and whether you can kind of make these assumptions. And this was a collaboration with Kirsten Voorhees at Harvard Pilgrim, Christoph Lang, my old mentor at Harvard School of Public Health, Steen van Steelant at Ghent University in Belgium, and John Hokinson at the University of Colorado Anschutz through my K award, which was looking at genetic overlap of cardiovascular and pulmonary disease. And then my National Institute of Mental Health R1, looking at the role of sex and genetic association studies of depression.